Welcome to Ask and Learn.
So P is giving the performance of someone learning a topic. So it would make sense that at the very start you pick up a lot of the material really quickly. So when in terms of time, we can think about this as P is increasing most rapidly when T is small. So I want to put these two together. And as the change of the performance over time, well, since it's increasing most rapidly at the beginning, we would expect that it to slow down at the end. So we can say that dp by dt should go to 0 as t goes on, so goes to infinity. And now, if we're told that m is some maximal level that anyone should be able to perform at, if we want to see if this differential equation actually does give a good representation for the learning model, you might want to first start by just solving for what P is. So let's go ahead and do that. So the first thing I'm going to do is, you might look at this and notice that this is a separable equation. So I'm going to go ahead and try to get all my P's on the same side as my derivative here, since I want to group all the same terms together. So I don't see any T's anywhere, but I do see these P right here. So I'm going to go ahead and divide by M minus P. And when I do that, I end up with 1 over M minus P dP over dt, and it'll just be equal to K. Okay. Now the next thing I want to do is move my dt over. And when I do that, I end up with 1, or I'll move the dp up here. So dp, and let me erase this. Oops. So dp over m minus p is equal to k dt. So when I'm integrating this, m, since it's just some maximum level, this will be a constant, as well as k, we're told it's just a constant. So if I integrate each side of this, so the right-hand side will just be kt plus some constant c1. And if you look at this here, you may notice that it looks very close to a natural log's derivative, because I have p up here and then I have p in the denominator. So I'm going to write natural log of m minus p. But if you were to take the derivative of this, you would end up with it being negative. So I'll also need to throw on a negative here. And you can see that if you just do a u substitution in for this instead. If you let u equal m minus p, you can also get this here. All right. So I have this. Now I want to solve for what p is. So the first thing I'm going to do is move the negative over. So I get natural log of m minus p is equal to negative k t minus C1. And then I'll go ahead and move this up here. Now what I need to do is exponentiate each side. So put each side to a base of e. So the left-hand side will cancel out. I'll get m minus p is equal to e to the negative kt minus c1. And then since I'm solving for p, I would add p over and subtract this. And I would end up with p is equal to m minus e to the negative kt minus c1. All right. So now let's maybe rewrite this a little bit so it can look a little bit prettier for us. So remember that when I have exponents being added or subtracted, it's the same thing as the base of those exponents being multiplied. So I can write this as negative e to the negative c1 times e to the negative kt. I'll just go ahead and call this e to the negative c1, since it also is just a constant. I'll call it c2. So that gives me m minus c2. And then recall that when I have a negative exponent, I can just write this as 1 over whatever I have here. So I get e to the kt. So if you're looking at this, you may notice that as time goes on, that this portion here will go to 0. So as time goes on, so t goes to infinity, if I take the limit, m, since it's a constant, will still just go to m. But this here, so c2 is a constant, and ek to the t will get very large. So I'll have c2 over some very large number. So this here would go to 0. So it first makes sense that this could be a model, because we would expect that as time were to go on forever, we should reach our maximal level of performance. And the other thing that I should be worried about when I'm looking at this is this value here will always be negative. So this expression right here never actually outputs anything bigger than 1. So it would make sense to say that, well, before I start, I should always be below this m. All right. And if I were to sketch a graph for this, what this is really telling me is that this is a horizontal asymptote, because I'm looking at the behavior as this function tends towards infinity. So at m, I have a horizontal asymptote. And I can just go ahead and choose any value for c2 here, since it just wants a possible solution, which just means I can choose c2 to be whatever I want. So I'll just go ahead and make this so that c2 is equal to 1. And when I do that, I end up with m minus 1, and I'm just going to do that for convenience. And then you can see that this will tend towards it like that. So this is one possible solution if you were to just pick some random number, but it would make a lot more sense for us to actually start at 0. So if c2 is actually m, so maybe I should write that this curve here is c2 is equal to 1. if I have C2 is equal to M, instead, I'll get to start at 0 and then tend towards my horizontal asymptote again. So C2 is equal to M.